Well, this is lecture 2 in BENG280B, and today we're going to talk about image quality. Some of this, for some of you, will be review from 280A. The best reading for this is Prints and Links, chapter 3, from sections 1 to 5, and also Bushberg, the entire chapter 4 is relevant. If you want to look at the 280A lecture, it's here online on YouTube, but we should be able to get through all the concepts today just fine. So here's a list of essentially the big concepts in image quality, and we can just go down the list one by one. Spatial resolution is just, is the image blurry or is it sharp? You know, can you depict edges with great precision and points with great precision? Contrast is essentially how much signal difference is there between your target, for instance, a metastatic lesion in the liver versus its background, which is the normal liver. The concept of noise is random signal that's essentially added on top of the signal of your target, and you would like the ratio of the target signal to the noise to be high, and that's the signal to noise ratio. So if we have the mean value of the signal in an image is 100 for, say, that metastatic lesion, and the random fluctuation in that signal is 5 as we move across the lesion, then you have a signal to noise of 20. Contrast to noise is the signal difference between your target and the background divided by the noise. And then we'll briefly talk about temporal resolution. Basically, how fast can you take a picture, and can you freeze motion, for example? Is patient breathing or patient cardiac motion a problem for the imaging modality, in the sense that it would blur the signal over different spatial regions because of the motion? As we'll see, and we saw in the introductory lecture, there's a wide range of temporal resolutions in medical imaging, ranging from microseconds all the way up to minutes of acquisition time for these pictures. So it's a big deal to understand the resolution and how you can compensate for low temporal resolution. So let's start with spatial resolution. And if I have an object, my true object is this gold background, and I have a point in that object such that, the perfect image or the ideal image is something where I have a spike right at this tiny point. When I image that object with my system and I see that I get a blurred point, it has some width, and if these are the pixels, it covers a number of pixels in 2 dimensions. This function, the image of that point object, is called the point spread function. Let me put on my laser pointer here. And it has a spatial dimension or a spatial width. And so characterizing the spatial resolution of your system with that function is complete, but you can also, if you know the functional form of the point spread function, let's say it's a Gaussian, and we'll look at what that means. You can give, say, the full width at half max, and that gives the entire description of the point spread function if you know its underlying analytical form. So this is often used to characterize images or imaging systems and their how much they blur a signal. If we go to 1 dimension and take a look at a point spread function, and Prints and Links, they use H as the symbol for the point spread function. And here we have an imaging system in which I've got 2 targets, one at x1 and I have one at x2. And the point spread function makes the image of that very small target at this point this blurred function, or this Gaussian. And it's characterized by a full width at half max, which is given in millimeters, and it's however many millimeters wide this function is when you're 1/2 of the way from the peak down to the base. Here, the point spread function is shown as an identical function, just displaced by either x1 or x2 from the origin. And most imaging systems we will model that way. We'll say that the point spread function is not a true function of position in the field of view. It is the same everywhere in the field of view. That makes life a lot easier. For the most part, it's a good assumption. It's not perfect though. Some imaging modalities do have much blurrier spatial resolution, say far away from the transducer in ultrasound, or in CT, your best spatial resolution is close to the center of the scanner, and it decreases as you go out. But for the most part, we can, if we're over a small field of view, we can assume this is true. As the objects come closer together, we ask the question, can you still resolve that there are two objects there? That's one way to characterize spatial resolution. You say, well, how close can I get 2 point objects such that I can determine that they are 2 points with certainty? And as these objects get closer, and if this is a Gaussian, and now their separation of the two objects of our two targets is equal to the full width at half max of the point spread function, then the resulting image is the summation of those two, and you get this, so it's kind of a flat top object like that. Now, I really can't tell you when I look at that picture whether or not that's two dots, that have added up to this flat top, or one flat top that's been blurred, right? So you really can't distinguish those two things anymore. And you say we're kind of beyond the spatial resolution of our system. And that's why this full width at half max comes in handy. You know what this separation is. Finally, if the dots are really close together, you just get a single blob, and there's no resolving those things anymore. Interestingly, in super resolution microscopy, if you have an object here and an object here, and or even here and here, and they're, say, fluorescing, but they're fluorescing at such a low rate that you can detect the photons from this as basically a separate event from the photons from this. You can, by doing a temporal analysis of your signal, detect where the mean value of this fluorescing object is, even though it's a spread out value like this, and you can create super resolution images where you plot the mean value of these point spread functions. We don't usually do that in any medical imaging modality right now. So here's the point spread function in 2 dimensions. Now, recall, if you made this also in the slice direction, for example, in the 3rd dimension, it would be a ball of in this case, redness, with a central part that's the brightest or the reddest and falling off. For a lot of medical imaging, we just assume that the slice contains all of the signal we're interested in to simplify our life. But of course, that's not entirely true. The z direction of the slice direction itself will have its own point spread function in that direction. In general, there's a 3D point spread function. If I, for say an X-ray imaging system, I put on my imaging plane a very thin wire, I can get a line spread function. And what that does is it takes away the dependence in this direction. It's a constant signal in this direction. And so when I'm only evaluating my spatial resolution in one dimension, it's along this line, since it doesn't vary in this direction. And that gives you your line spread function. And an edge spread function is when I put let's say a square down and look as I go from the background into the square, what that resolution is called an edge response function. Most of what we're going to talk about is the point spread function, and it is a the most practical way of telling somebody about an imaging system in the fewest words. It's this spatial resolution. I'm going to pause here and just talk about Gaussian functions. Those of you, you're grad students, and so you've all used these functions, but let's just review it. This is a Gaussian. It's e to the minus 1/2 x minus x bar, where this is the position or the mean of the peak of the Gaussian, over sigma, and sigma gives you the width, essentially, of this function. As sigma gets smaller, right, this thing gets narrower, and it gets taller. This is 1 over sigma here, so the whole thing is taller if this is normalized. The integral of this thing from minus infinity to infinity, integrating over x, is 1. And it gives this beautiful shape, right? This function is used a lot. It's used often to actually give you a functional representation of the point spread function. So if my object is here, and my image looks like a blob, oftentimes that blob is encoded or given as a Gaussian function. We will also see that statistically, if you look at a noise field, the frequency of certain values around the mean of the noise field can be given as a Gaussian, and in that case, it's called a probability density function. And again, sigma is the root mean square deviation or the standard deviation. Sometimes I'll call this standard deviation. Sometimes I'll call it RMS for root mean squared standard deviation. And these are the formula for the mean and the standard deviation squared. This is called the variance, which is the standard deviation squared. Okay, so that was just an aside. You have to know about Gaussian functions. I'll call them normal distributions or Gaussian distributions. Now let's go back to our signal and consider the Fourier components that are that go towards building our image signal. So again, in this example, we have a one-dimensional image. So this is position in millimeters. And our image looks like a square function, right? Like that. And it turns out that this function with the wiggles in it that looks like a square function can be constructed from 4 sinusoids of progressively larger or higher frequencies. And those 4 sinusoids only, with relative amplitudes given in this diagram, when you add them together, you get this approximation of basically a rect or a square function. You should think about this all the time. I mean, every function in the plane can be decomposed into its Fourier components. That is, the amplitudes and the phases of sine waves that can be used to reconstruct that signal. And the reason it's useful to think about that is, for those of you who've taken MR, you know that the data is obtained in Fourier space. And otherwise, it turns out that most imaging systems will operate or attenuate spatial frequencies differently depending on their frequency. So the system might attenuate this red frequency more than it does this very large or low frequency purple signal. And we're going to go through an example of that. And so this is just to remind you that you can construct any signal in 2D, 3D, in this case 1D, with Fourier components or sine waves. So why is that useful? Well, it's very useful when we think about this. And what's happening here is we have a signal that is 1 cycle per millimeter. It's a sine wave with 1 cycle per millimeter. Sometimes this is called 1 line pair per millimeter, because if this bright signal is a line, say over here, I've got a line and another line, then they're going to be 1 millimeter apart. So it's got line pairs per millimeter. 2 cycles per millimeter and 4 cycles per millimeter. So they all have these 3 signal inputs that are going to go into our imaging system and come out the back end. They each have the same amplitude, but progressively higher frequencies, spatial frequencies. if we put this signal into our imaging system, and this is what it looks like going into the imaging system, and this is what it looks like coming out, right? We can graph that as follows and take note that the amplitude seems to have been diminished or attenuated by our imaging system. And at this frequency, we have 87% of the amplitude left when we push this signal into our imaging system. So if I measure the contrast between this dark trough and this bright peak, I'll get 87% of what I had originally between the dark trough and the bright peak. And then as the frequency increases, we push this through our imaging system and this comes out, right? And we can see that our imaging system has reduced or attenuated this frequency by a greater amount. I'm now at 56% of my original amplitude when I measure the contrast between a bright and dark. So my bright peak, my dark trough, bright peak, dark trough. And this goes on. As my frequency gets higher, the attenuation gets higher, until finally, I'm down to this very unusual pattern on this side. And finally, I just have a mean value. It's like all of these have been averaged together and they come out as something that doesn't change as a function of position. It's just a mean value. And that's the true cutoff. We no longer can image frequencies that are this high. Okay? And if we want to quantify this behavior, so this is the behavior we're measuring of our imaging system, and we'd like to mathematically quantify that behavior, we can turn to something called the modulation transfer function. That function characterizes our system completely in terms of the spatial resolution or its ability to resolve things as a function of higher and higher frequencies. We plot as the independent variable here, the spatial resolution or spatial frequency, in this case in cycles per millimeter. And we measure on the system, we make these measurements that this frequency is attenuated to 87%. This one at 2 cycles per millimeter is at 56, and 4 cycles per millimeter is at 13%. So here are 3 data points. If I fill in all the data points in between, I see a function that looks something like this. And it's called the modulation transfer function. As we go to higher frequencies, the attenuation gets larger. So you can imagine if I show you this functional form and I've labeled this axis correctly, then you know pretty well how that imaging system is going to resolve small objects. A system that rolls off very quickly down here obviously will blur things, and you just won't see frequencies at these values, versus a system that has a modulation transfer function that goes out here, that will still be resolving sine waves out at these higher frequencies. Now, is there a single number you can quote to say, okay, I have essentially characterized the system? Well, one possible number would be, the 50% mark of this function. If you knew its functional form, you said, well, what's the half height of the MTF? We go down here and say, well, that's 2.2 cycles per millimeter. That's a sensible proposition, but most manufacturers don't do that. When they give you this MTF, they will say, we can resolve things to sometimes to 1%, 5%, 10% out here. And that gives them the ability to give you a higher number, which is say 4.2 cycles per millimeter. So when you are, asking, well, what is the MTF of your system for whatever imaging system it is, you need to know what this cutoff threshold is that they're giving you. Oftentimes this function is a Gaussian, right? It is well characterized by a blob kind of function that is well modeled by a Gaussian. The other interesting thing about the modulation transfer function is when you take the inverse Fourier transform of this, you get the point spread function in space. Remember the point spread function was in X and Y in space. Let's go back and take a look at it, right? So it exists here as perhaps a Gaussian in X and Y. And when you take the Fourier transform of this thing, you get the modulation transfer function. So you can test the resolution of your system in a couple of ways. One is put a really tiny object in the system and image it and see what that picture looks like. And that way you directly measure the point spread function. And for CT, a little tiny object can be the ballpoint out of a ballpoint pen, for example. For magnetic resonance imaging, those little tiny capsules of vitamin E, we used to use those sometimes. For nuclear medicine, same deal, one of those little capsules, but you have to inject it with a radionuclide, something that has some radiation coming out of it. And for echocardiography or for ultrasound, oftentimes they have a gel with tiny little beads in it, and you can measure the size of the beads as a function of position in the gel. So those are ways of directly measuring the point spread function. Okay, so going back to characterizing our signal and our system with Fourier components, let's look at this example where we have a signal that has a DC component, like a background value, and then we're going to add a modulation on top of that DC component, and that modulation comes in the form of a plane wave or a sinusoidal oscillation. And A is our DC background value here, and B times this sign gives a modulation around that background, right? And for different ratios of B to A, so 0, 0.2, 0.5, and 1, we get these different images. In that, here we're adding 1 to the background, and here we're subtracting 1 from the background. So you can see this is a low contrast sinusoidal variation. This is a higher contrast and a much higher contrast, okay? And so that's one way of characterizing the modulation that a plane wave makes on your image. And when we look at medical imaging systems and ask, well, for a specific sine wave that goes into our medical imaging system, it gets modulated, as we saw, by the MTF. And the MTF, in this case, in the Princeton links nomenclature, the MTF is this function capital H. It's the Fourier transform of that function little h that they had in the other illustration. And so what happens is when this system goes through, the DC component gets modulated by the modulation transfer function at 0 at the origin, right? And the sinusoidal component gets modulated at whatever frequency it's at. So it's the modulation transfer function at that frequency. In this case, it's 1D, so we only have it at this frequency U sub 0. And this is how you can quantify what is occurring with the sinusoids that are creating your signal. And so the final output is, where your contrast before was B over A, it's now B over A times the modulation transfer function at that frequency divided by the modulation transfer function at 0. So that's how it's encoded. How do you measure it directly? If you want to measure the modulation transfer function directly, you can make a phantom that has parallel lines, and they have line pairs per millimeters or cycle per millimeter, and they can get closer together. And so you can just build a phantom that has this pattern inside it, as say in CT, they can be little aluminum pieces. In MR, you could do it with, plastic where you had water in one and plastic in the other, etc. Another favorite is having these star pattern phantoms, and what shows up in the picture when you image this is as you get closer to the origin of the star, eventually this just blurs into one signal, and you can measure the essentially frequency at which that reduction of the signal into a blur occurs. Here's an example of one of these phantoms. This is for CT, where we have parallel lines of increasing spatial frequency as we go around this circle. And the point of this paper, I pulled this from a paper, was that we see essentially the modulation transfer function here. If I measure the contrast between the dark line and the bright line, they claim that with their modified reconstruction technique, they get higher modulation here. And so the value of the modulation transfer function at this spatial frequency is higher with their reconstruction than it is with the standard reconstruction. In general, you look around this curve and see, okay, I can't really determine anything anymore. There's my cutoff frequency. So you just directly measure the modulation transfer function. And then these intermediate points here will give you those intermediate points between 1 at the origin down to 0 at the highest spatial frequency. Okay, now we're going to look at trading off spatial resolution for signal to noise. And here's a function that we have from our imaging system, say, where this is the pixel number across the field of view. Again, we've got a 1D function here. And here's the grayscale value. So it can be any kind of image we want. And we'll say this is the liver, the background liver or something. And as I move across the pixels, I see that they have this variation around some mean. Okay, so the mean value is like about 55. And I have this variation. If I would like to make my picture look less noisy, what I can do is average neighboring pixels together to get a better estimate of the mean value over local regions and reduce the amount of sort of root mean square deviation of that signal. And that's called convolution. You have some convolution kernel that calculates the average value to get this point. And that could use say 5 points. It uses this one, this one, this one, this one, and this one. We weight these points together to make a new point, which is this one, which is the mean, approximately their mean value or their weighted mean. Move to the next point, do the same thing with these points. And that gives me a much smoother, cleaner looking image. The problem with that, obviously, it's fine if you have something that doesn't change as a function of space, but if we had an edge, that smoothing is going to blur that edge. So here's our, sorry, I had graphics for this. Here's the target point on our output, and these are the input points to our convolution kernel. It gives me the new value. So let's take a look at that in practice. So here is a CT image that's acquired with very few photons, and the reconstruction algorithm, in order to make a reasonable looking picture, actually averages the data together before making the reconstruction. And so you can see with this resolution phantom, this is a phantom that we had built in the machine shop here. At a certain spatial frequency, these things are perfectly fine, but then as we go down to higher and higher spatial frequency, basically it blurs into an averaged value. This is the image when we use, approximately 5 times the amount of photons, and therefore the detector array doesn't have a ridiculous amount of noise on it. We don't do as much averaging over the detector array, and now we can resolve these finer lines. If you go back and look at that, here's the noisy one, and here's the less noisy one. So essentially, what's happening is when we're trying to keep the root mean square deviation, or the amount of noise in the field of view, to a respectable value, which happens here, we blur the picture. And this is the decision of the engineers making the image, right? It's like, how much blurring do you do in order to make the picture have a background that doesn't just look like random numbers versus losing detail in your picture? And a lot of it depends on how much detail you actually need in your picture. And then, of course, there's the choice of just imaging longer, making averages so that you can have a reasonable looking picture with a low noise value or low random noise value, and not do spatial averaging. So we can plot what this looks like. Here we have the contrast, right? So this is a modulation transfer function again, where we get the amount of modulation on the signal for this spatial frequency or separation of the dots. And we look at it after we've had to do averaging to keep this noise value reasonable. We can see we pretty well lose all the detail in that feature. We still have this feature, but that feature has been sacrificed. So this is just an example of some convolution kernels that are used when trying to optimize the signal to noise required for your picture. And so the simplest, obviously, is just a rectangle. That means you take 5 pixels around your target pixel and average them together, right? And that gives you a new pixel value. Here's a convolution kernel that says, well, take your pixel value, that goes in as 50% of the average. And then as we move to the side pixel, this will be 20% of the average, and this will be 5. And that'll give you a more central or centroid kind of averaging. And then there's this, which is basically a sinc function that averages this with actually negative values, or a trough on the outer points. You wonder, like, why would you ever use this one with the trough? Well, it turns out the Fourier transform of this sinc function in the spatial frequency domain is itself a rectangle. And so what it does is it cuts off frequencies above a certain amount and just cuts them off directly. Whereas this rectangle filter or convolution kernel in the frequency domain, it's actually a sinc function. So you get a very interesting degree of summation of spatial frequencies that are, weighted as a sinc. So oftentimes this type of convolution is used to both downsample and upsample images when you need to change the resolution. Here are some example 2-dimensional convolution kernels. This is a Gaussian, and that is it rides up to a peak in the middle and then rides down. And so you could smooth an image or reduce the noise in an image and perhaps increase the signal to noise, between a very large object in the background by convolving with this. The nice thing about this is it's also well behaved in the Fourier domain because its Fourier transform is itself a Gaussian. This convolution kernel gives you a first derivative in the x direction. This gives you a first derivative in the y direction. And then this is a second derivative, etc. And then these combinations of these derivatives are down here. And so if you're looking for edges, if you're looking for peaks and things like that, then these different derivatives come in useful in terms of convolving your image. So let's look at the original or the effect of some of these filters and convolutions on a medical image. Here's an X-ray image. This is just a plain film X-ray image of somebody's knee. And the original picture looks like this. If we convolve this, say with a smoothing function like that Gaussian, we get a blurry version of this picture. And so random noise in the background goes down, but you can see also the edge detail here gets blurred out, and the edge detail up here gets blurred out. If we look at amplifying edges, and that is we convolve with those filters that actually look at the first derivative, then you can start to see these images in which the edge itself is enhanced. So the power, the contrast of the edge features becomes enhanced until finally the mean value of the background from a full on, this looks like a first derivative filter. It basically doesn't detect a derivative here. This goes to 0, and the only thing detected is the edge. And so this is when you're going to break straight up edge enhancement. These tend to be quite noisy, these images. These tend to be less noisy in terms of characterizing the noise as just random signal. So let's look at noise. Perhaps we should have started with some noise, actually. But here, this is a series of MRI acquisitions in which the number of averages used to make the acquisition has been reduced to going from here to here. And so this might be obtained with, say, no averaging, just a single acquisition per each phase encode pulse, 2 acquisitions per phase encode pulse, 4, and then 16 acquisitions per phase encode pulse, and you get a very high signal to noise image. That is, the signal, which is the underlying true value or true image in this sagittal head, is here, and the noise is this hash on top. So the ratio of this signal to the hash has increased as we average. How do you quantify this, in your head? Like if I was to say, okay, tell me what the signal to noise of this picture is, could you do that in your head? Do you know what that means? Do you know what this means? Is the signal to noise of this 100, or is it 1? Is it 0.5? You'll be able to do that by the end of, I hope by the end of the lecture, actually, but certainly by the end of the course. This is high signal to noise. This is low, just in case you're getting the polarity wrong. Okay. You can, for a specific noise level, signal to noise level, as we said before, if we blur with like that Gaussian kernel, we will actually increase the signal to noise. In the sense, if I take an average value here and divide it by the value of the noise measured from the background, I will get a higher signal to noise value than I will for this image. However, it comes at a cost. It comes at the cost of blurring the image, as we saw before with the X-ray example. And here you can see the very fine features of the cortex, etc. As we blur or convolve, we lose those fine features down here. Let's say these fine features at the bottom of the tongue all get blurred here. So depending on where you want to operate in terms of spatial resolution and signal to noise, you choose your appropriate blurring filter, or another way of saying it is your appropriate MTF, because you can essentially filter your image after taking it to achieve an MTF. Here's an example of high signal to noise CT, lower signal to noise CT. And this is a factor of 12 in X-ray radiation, okay, going from here to here. So this brings up another question: is if your task is to differentiate the blood pool from the myocardium, is it worth taking 12 times as much radiation or giving 12 times as much radiation to the patient to get to here? Your signal to noise is much better, but is your signal to noise good enough here? Well, that question is answered by it depends. It depends on what you want to do with the image. And so if you want to detect a very tiny object, right, with great certainty, then perhaps you need this signal to noise. For example, is this little dark dot right here, is that an object floating around in the ventricle? Well, when I go to the high signal to noise, I realize it is not. It's just a random dark signal here. However, if all I want to do is tell you the volume of this left ventricle, this image is just fine. So it is task dependent. And we'll come back to this concept again what your signal noise has to be, what your spatial resolution has to be, is task dependent. Okay. Oftentimes, to essentially demonstrate for an imaging system what the performance of that system will be at a specific resolution and a specific signal to noise, a contrast detail curve can be created. And this is often done in CT. And so if this is the contrast detail curve, when we use a lot of radiation, so we can detect all of these objects quite easily when the contrast between the object and the background is bright, i.e. there's a high contrast. As our contrast gets lower, it gets more difficult to detect these objects. Obviously, even with high signal to noise data, you'd be hard pressed to say if there's an object here or not. As the contrast to noise drops, this curve, this contrast detail curve, when you say, well, you know, there's a point beyond which I just can't tell you whether or not an object is there. Here it looks like we get basically the top three small objects here at this contrast level, but we're not going to get these ones. And then at lower contrast to noise values, this one drops out too. So does this one, drops out. And so this contrast detail curve essentially characterizes your system for this task. Okay? And you know, essentially you just have to give somebody this curve, right? And it's not terribly convenient to carry this curve around, right? Because it kind of depends on what the contrast is. And so most of the time, curves like this are used when you are evaluating, say, relative reconstruction techniques. You would have a contrast detail curve at one reconstruction technique and then another reconstruction technique and see how much it moved it. But if you de novo ask someone, well, you know, what is the spatial resolution of your CT scanner? They don't usually pull out a contrast detail curve, right? Because it's a little too awkward, right? Okay, so let's figure out, how do we characterize what we can see that the noise in the background of this image is far less than this, which is far less than this. So the question is, how do you characterize the level of noise in the background? Not just the background, but also the level of noise inside your target, right? Then sometimes your target gets so small, like these targets down here are so small that they could just be noise, the whole target, right? And so, you know, what is the root mean square deviation of the pixel values inside here and outside here? That's called the noise level. Let's go back to our Gaussian function. This is called a normal distribution, and most random things in the world that are modeled by scientists are modeled with this function. It's called a normal distribution. Again, it's this formula, right? And in this case, we have observations, right? Or say just pixel observations, number of pixels, right? And we say, well, what fraction of pixels in the background do we get a value of 40, you know, or 40 plus or minus some bin width here? And this says, well, you know, you get 5% or 4% of your pixels are at 40, right? There's some width here. And then as we go down in numbers, say, well, how many pixels did we see a value of 20? Well, that's 0.005, so 5% again, right? This distribution is called a probability density function, right? The integration of this is 1, so 100% of your observations are contained in here. It has a mean, and that's given by this. You know, you compute the mean quite easily just by summing up and divided by the number of observations or the value of the observations. And it also has a sigma value. This is called the variance, and the square root of the variance is the standard deviation. And so that's sigma. So how do we measure sigma in a picture? I will come back to this. Here, the way we can do it is we just draw a boundary around some place that we know is all background, right? And we say have a 10 by 10 pixel dimension object. And so it's 100 pixels. And using those 100 pixels, we'll measure the mean. And from the 100 pixels, we'll also measure the sigma value. And that gives you the signal level and the standard deviation of the background. And you do the same thing in your target. This gives you the signal level in your target and the standard deviation of the target. And now we have all we need to measure or characterize the contrast to noise. What we're going to do is we'll take the signal difference between these two regions, which is the difference between these two things, and divide by the sigma value. And if the sigma is the same for here and here, we can just use one sigma value. Right? So in this case, you know, the mean is say 100 and the noise is 10. So basically we get signal to noise around 10, although that sure doesn't look like 10, to be perfectly honest. Here's an example on a CT scan. Remember this phantom where we're looking at the spatial resolution by looking at the line pairs. Here we're just going to look at the contrast between a target, which itself is a hole in the phantom, and the background of that hole is plastic, and it has a different attenuation value than air, which is what's inside the hole. So we can measure in the background. Remember, we had the high signal to noise image, and we'll measure the root mean square deviation in that background. Here's the histogram of all of the pixels contained inside this area, and we measure that sigma b is 3.4. That's what that width is there. And the mean value of this background is 195. In the image in which we obtained it with much fewer photons, and we had poorer signal to noise, when we look at the root mean square deviation of the same background, we get a bigger number, right? The pixel values are varying around the mean more. We get the same mean, basically, because it has the same value as it is the plastic, so it has the same value. Obviously, if you get more and more pixels, the two means will approach each other, right? Because it's the actual mean. But here, obviously, the signal to noise is lower because the sigma value got bigger. And so we can calculate what is the value of the target at its position. And so we measure that by drawing a line through there. We measure the value of the target on this one by drawing a line through here. And in this case, we get a much lower contrast to noise value for this one. A couple of things happened, obviously. The background RMS got higher, right? That's going to drop the contrast to noise. But also, the value at the minimum of this small object got closer to the mean, right? And the reason that happened is because the spatial resolution of this picture is also lower, right? So you don't have a very sharp object here anymore. And so the depth of the contrast of that object isn't as high as it is over here. So contrast to noise is a really nice, simple number to give somebody when you're asking, like, say you want to do a segmentation task and you're segmenting a tumor and it's in a background of normal gray matter in the brain. And you say, okay, well, do you think we're going to be able to segment that thing fairly automatically? And you can say something like, I think so, because the contrast of noise is 10. And so it's going to be pretty easy just to pull that thing out. If you said, I think so, because the contrast of noise is 2, then your advisor would say, well, that's not going to work because 2 is not enough. And so it's a simple representation of the image quality for that task, which is pulling the signal out from the background. So here's an example of signal to noise, true signal to noise values, if I believe the author here, where this is 0.5, this is 1, and this is 2 signal to noise, right? So when you look at the profile in 1D, since it's sort of easier for us to look at a profile and picture the noise value, you can see the object goes up to a new mean value, and then the background's down here. So this is an example where the noise value is constant and the signal is changing. Okay, so the only thing that's happening really is my contrast between the background and the signal is increasing. Okay, so I go from here to here. The random noise value stays the same. It has the same signal value. Here is an example where the signal changes as we go up this ramp, right? And the noise value stays the same at each signal level. And this is characteristic of magnetic resonance. The noise value on MRI, barring any weird artifact or other artifacts, should be independent of the position. That was true almost universally in the first 25 years of MRI. Now, though, people are using multiple coils in different parts of the image to image different parts of the field of view. And so the actual noise value can vary from region to region. We won't talk about that in detail. I think in 280A, Dr. Liu probably talked about, fast imaging with an array of receiver coils. But for the most, if you use a single coil, you get the same noise, as it doesn't really matter where you are in the picture. In this case, we see that for a lower signal, for a medium and high signal, when the signal's high, you have higher noise than you do for a low signal. And this is the case in X-ray imaging, because the high signal in CT is the regions in which there is a lot of photon attenuation. And so you don't have as many photons to count. You have less precision in counting those photons, and the amount of noise in that region of the image goes up. Right? Looking at temporal resolution, going back to our first lecture, this is the only thing we're going to talk about in terms of temporal resolution. This is a topic for a whole course, right? Because remember, when we looked at the time it took to create an image over all of these, imaging modalities, it was remarkable in the amount. I mean, X-ray fluoroscopy, you're basically making a picture every 5 microseconds or so, or the exposure time to make one frame can be down, in the microsecond range. You take these flashes, each one of these fluoroscopy images is kind of a flash image, and then you play them back at 15 to 30 frames a second, because there's a long delay between each one of those flashes. Echocardiography or ultrasound is somewhere in between. Here you can be imaging at about 30 frames a second, right? Such that the exposure, the detector is open, for 30 milliseconds, and you play it back at 30 frames per second. However, if you want to scan over a whole object and create a 3D object, that oftentimes takes about 3 seconds to do that whole scan. If the object doesn't move in the 3 seconds, then when you play it back at 7 frames per second, it looks okay. However, when the object moves quickly, this playback will have artifacts in it. Then we can look at computer tomography, which is somewhere in between. There's 140 milliseconds to get all of the data you need to make a frame, and that can be played back at 10 frames per or 7 frames per second. However, the volume you are acquiring, the pixel volumes you're acquiring at this rate are extraordinarily small, right, compared to everything else. So this is super impressive to generate pictures with this spatial resolution at this rate. Remember, when you're doing X-ray fluoroscopy, you have very good in-plane resolution, but it's a projection of the whole patient, right? It's very thick in one direction. Nuclear medicine, well, let's do MRI first. We'll go in order. 2D MRI, about 12 seconds to make a really nice 2D MRI picture, and with this kind of spatial resolution in millimeters. And you can play that back. If over the 12 seconds, let's say you took 12 heartbeats to take your picture, and you averaged or you collected data over those entire 12 heartbeats, when you play it back, you're going to play it back normally around 25 frames per second. And so if everything goes well, patient doesn't breathe, your gating is perfect, you can piece together all that data such this 25 frames per second looks really good. It looks like a movie obtained at 25 frames per second. And it, things pop out, details pop out for these movies. They're fantastic when they work. 3D MRI obviously is a lot longer, right? Because you have to do this not just in one slice, but in how many? 64 slices, something like that. So, most of the time when you do this, you take quite a bit of time to do it, and you compensate for motion. And nuclear medicine has an extraordinary duration to acquire images, right? And 250 seconds, so it's many, many heartbeats, many, many breathing cycles. It is binned through the heart rate and normally played back at 10 frames per second. But when you're taking 250 seconds to make it, a lot of things can happen, right? So there's a lot of other motions that can occur physiologically to blur that picture. So extraordinary range in temporal resolutions. The two types of temporal resolution are how quickly do you flash your data into the system versus how quickly do you play back these time frames. And then sometimes you're collecting data for the whole time, and sometimes you're only collecting data for a very short period of time during the acquisition. So given those numbers, we can look at some of the effects of having low temporal resolution on artifacts and images. And again, this is a field that is a cottage industry, basically. It's like, how do you characterize artifacts, motion artifacts being one, and how do you get rid of them? But you can see on the left here, there is a basically an axial image, containing the liver of a patient, in which the patient in MRI was allowed to breathe just, at will, right? So there's no gating to that person's breathing. You can see a couple of things. One is there's a lot of blurring of features in the patient's, chest and in their abdomen. If you look at the relative blurring of these objects versus, say, something that's fixed, like their spinal cord. And then there's also these replicants of the chest wall. And these are called ghost artifacts. And so both of those, features, both the low resolution and the blurring and these ghosts, are a result of not being able to image with high enough temporal resolution to freeze respiratory motion. Okay, so, or ask the patient, for that matter, to hold their breath for 10 seconds. So if you say, hold your breath for 10 seconds, you can get this picture. And now we're fast enough to achieve making an image in the time that a person can hold their breath. But you can also see that these replicants of the aorta, this is the descending aorta, and then these are replicants of the descending aorta. The reason they occur is because the image was taken over, say, 12 heartbeats. And so there's a periodic change in the signal intensity in the aorta over those 12 heartbeats. And that periodic change shows up as these replicants in the feature. Okay, so this feature, as the data is being acquired, is kind of blinking on and off as the flow goes through. And so it's brighter when the flow is coming into the slice, and then it's a little darker when the flow is or the blood is stationary and staying in the slice. And that creates this. So that's not a blurring. However, over here, you can see there still is a blurring. And that's basically the heart is moving the tissue. You know, it's sitting over here and it's moving the tissue up and down, causing the blurring on the side. And so you need to, at these levels, when you're asking what's the temporal resolution of MRI, you need to be able to compensate for both breathing and cardiac motion and lock the data acquisition into phase with both cardiac and breathing. Right? When you do that, you can share the data between those heartbeats and share the data at different phases of the respiratory cycle, or get the person to hold their breath and get rid of that effect of low temporal resolution. Here's another example from PET scanning in which the liver of this patient in the PET data looks like it ends here, right? And you have this metastasis, which is the point of this scan, is to determine whether or not you have mets that have gone to other parts of the body. This person has colon cancer. You want to know what stage are there metastases? Where are the metastases? And so here it looks like it's outside the liver. However, when you turn off the correction from the CT acquisition, it looks like it's back in the liver, right? This met here. So both of these mets are in the liver, even though this one looks like it's well outside. And it's because of the different respiratory position of the PET data and the CT data that was used to do the attenuation correction in the reconstruction of this picture. You can see the picture's better in many places, however, gets the location wrong. And so there, again, it's respiratory motion. Can you acquire all your data at the same respiratory phase or within a breath hold? And in this case, obviously, it's no. And that's probably not going to be the case for PET for some time. So you need to do some kind of correction. Here is an interesting correction. Let me see. Of CT data. Now, the features I want you to look at are this, which is the right coronary artery. It's basically a bright circular object, and when the patient's heart is beating, you can see that it changes its functional form or its look considerably depending on what phase of the heart cycle we're imaging it. So we probably have 14 phases over the heart cycle, but the data is obtained over these 140 millisecond intervals. In that interval, this vessel is moving a considerable distance and causing a picture that is not the vessel, right? You know, it doesn't look like that. It doesn't have, there it's sort of stationary. When we go here, you can see the vessel is an arc, right? And we go to a different phase and the vessel looks like it's got two wings and a body, etc. Right? And then there's another arc, and then it's stationary again, and then there's another arc. So that's called motion artifact. And the problem there is we're not acquiring the data fast enough to claim that we're freezing this motion, right? However, if you have a model of what that motion is, and you know what that motion does to the object in terms of, you know, the type of picture it'll make and the artifact it'll make, you can take it away, right? You can modify your raw data to take away the motion artifact. And so here, this is after motion correction has been applied. All the raw data is here. We apply motion correction to it and then reconstruct that. and now you have a very clean moving signal, right? And so one could claim at this point, okay, if I know what the motion is, then I can model it in my reconstruction, and my true temporal resolution has increased substantially because every one of these pictures has a very good representation of that artery. And now it's incumbent on the person who's making that motion correction algorithm to then do some kind of phantom test to show that, in fact, the motion correction image is the true image. It's not just some other artifact image. Right? So, however, you can go a long way if you have a really good model. And this is what, imaging engineers at companies and in academia do this all the time. They take pictures that look like this and they say, well, I know how that went wrong. I'm going to create an algorithm to correct it, and they get pictures that look like that. And then this is the patent and the product, for imaging.